So some rules when naming these compounds, whether they be an alkyl halide or an alcohol. When you are using this substitutive convention, the way in which I told you, it's important that the parent chain includes the OH or the halide. We use X to mean halide substituent. What that means is even if the longest chain does not have the substituent, you will not use it. So if you look at the example below, if I wanted to determine the longest chain as normal, I would start counting in different manners. So if I use this chain, it would be 1, 2, 3, 4, 5, 6, 7 long. But if I numbered going the other way, it would be 1, 2, 3, 4, 5 carbons long. And in fact, if I check from the other side, 1, 2, 3, 4, 5 carbons. So normally you would say, well, this is a heptane. I'm going to use the one that is the longest chain. And for normal alkanes, that is correct. That is what you do. However, you have to use the chain where the OH or the X is directly connected. So here you can see that there's a carbon here, a carbon that spaces out where the OH is and where this main chain is. So the OH is not directly connected down here. I have to go to where the OH is directly connected, meaning I have to use this as my main chain. So the main chain length here would be 1, 2, 3, 4, 5 carbons, meaning it's a pentane. And numbering is always going to start from the end with the substituents. So that means here, if this is my main chain, I can start at either end. So that OH group is going to be at the 1 position. This is carbon number 1. So it gets 1 all. Now the rest of this we have to call a side chain. This side chain is 1, 2, 3 carbons long, making it a propyl. And it is on position 2 based on our numbering. So it gets 2 propyl. Now, when you are numbering, if you have both OH groups and halogen substituents, and also alkyl groups there, the OH group always takes precedence over a halogen group, meaning that if they're equidistant, or they're not equidistant, if they are, if you have to decide between which gets the first position and which gets a second position, or 2 numbers in general, the OH always is going to get the lower number compared to a halogen and compared to an alkyl group. So on this compound, this one is a little tricky again. Now, if you were to just count like normal, where you would think the longest chain would be, you might say 1, 2, 3, 4, 5, 6, 7. But again, we're missing our OH group, so it can't be that way. It's not directly connected in that way. So if we do this, 1, 2, 3, 4, 5, well, now our OH is directly connected, but our halide group is not directly connected. So there is a way that you can connect both into a chain, and that's if you start from this end, 1, 2, 3, 4, 5. So this chain connects both the OH and the halide group into the main parent chain. I know, a little bit tricky there. So this would be our main parent chain. It's 5 long. That's where they get the pent. Now I have to pick which side to number from, and as I just said, OH gets precedence, so we number from this end. This is position 1, 2, 3, 4, and this is 5. So our OH would be in position 1. That's how we get the 1 all. Now the two other groups that we know we have is a 5 fluoro, because there's a fluorine on the 5 position. And this side group, which is 3 carbons long, is a propyl, and it is on the 2 position. So how do we decide how to order these groups in the name? Remember that once you figure out the numbering for everything, it is then written alphabetically, and F comes before P. That's why it is 5 fluoro, 2 propyl, pent-N, 1 all. Now, another thing to pay attention to is that both alcohols and alkyl halides and other compounds are classified by what we call their substitution pattern. The question here is how many alkyl groups, that's carbon groups, are directly attached to the same carbon that has the functional group. So in this case, that has the alcohol or that has the alkyl halide. Now, again, what I'm asking is how many other carbons are attached to the carbon with the alcohol or the alkyl halide? The reason that we ask this question is depending on how many other carbons there are, it can affect the reactivity of the carbon. This is going to be very important when we start talking about reactions. So the substitution of that carbon will affect its reactivity, which is why I'm bringing this up. So for example, this carbon right here, it has an OH on it. Okay, so how many other carbons are attached to this carbon? Well, if we look, there is 1 other carbon right here. And then the other things that are implied as attached are hydrogens. Remember, carbon always makes 4 bonds. Don't forget that in our line bonds like this carbon still has 4 bonds. The other bonds that aren't shown are hydrogens. The hydrogens we don't write, but you need to know that they are there. Remember that they're there. Okay, so this carbon, again, is only attached to 1 other carbon right here. So it is a primary alcohol. This one right here, this has a bromine on it. Again, I want to look how many carbons are attached to this carbon. That's 1, 2. And remember, it has another hydrogen here. We're just not showing it. Okay, so 2 other carbons makes this a secondary alkyl halide. Again, depending on what type of alkyl halide or alcohol will affect the reactivity. Okay, so let's do some practice. Let's practice naming and then determining substitution level. So here I want to name the molecule that is listed and write the substitution level for any of the alcohols or halides that we have. So first, let's figure out the longest chain that has all of the alkyl halides or alcohols directly attached to it. Okay, so I can see if I go this way, this alcohol is directly attached, so I can continue going. Longest chain. This chlorine is directly attached, which means that I can go right here. This would be my longest chain I could draw where both the OH and the chlorine are directly attached. Now remember, directly attached means that there's a bond directly onto my highlighted chain, right? There can't be another space. So if this was something like this, right? If there's a carbon here, then that would not be directly attached, but this OH is directly attached. Okay, so the length of this chain is 1, 2, 3, 4, 5, 6, 7. So this is a hep-tan all, right? Because there is an alcohol here. Now we want to name the other groups on here. So I have to figure out which way I am numbering. Remember, if I go back here, that you're going to number with the OH group taking precedence over halogen or alkyl groups. So that means I will number as already shown where the 1 starts here. That means my OH group is in position 3. I have a chlorine in position 6, and I have a methyl group in position 4. So there's a 6 chloro on here, and there's also a 4 methyl. And our 3 is going to go here, right? Between the hept and the OL. So this will be heptan 3 all. So now I want to put this all together. Remember, alphabetical for any of the other side chains. So chloro will go first and then methyl. So in all, this will be 6 chloro, 4 methyl, heptan, 3 all. So there is the full name of this compound. Now let's talk about the substitution level. For our alcohol group, how many other carbons are bonded to the carbon on our alcohol? So let's get a better look at that. Here's the carbon that's attached to our alcohol. Attached to it are 1, 2 other carbons. So the OH is a secondary. This is a secondary alcohol, is how you would write that. For our chlorine, here's the carbon attached to it. And it is attached to 2 other carbons. So again, this is a secondary halide. All right, let's try another one. Here is some alcohols and halides in a ring. Now notice I have showed wedge and dashes. That's important because we have talked about in chapter 4 the ability to have these stereocenters, these chiral centers. And if you have a chiral center, you also need to distinguish its chirality. So we'll go and check for chiral centers at the very end, but this is just a hint that there are going to be potential chiral centers here. Now, if I was to draw this the same way, but with no wedges and dashes, I'm not telling you the potential positioning of these atoms in space. So you can't determine its specific chirality or its rotation, whether it's R or S, because I haven't given you spatial information. You need to know spatial information to figure out its rotation. You could still name this compound, you just would not include R or S determination. Okay, so back to the compound. This one is a ring. This is easy for figuring out the base. It has 5 carbons in it, so it's remember it's a ring, so cyclo, don't forget to add cyclo, pent for 5, and then we know that there's an alcohol here, so it's going to be cyclopentanol. Okay, now let's talk about numbering. Remember, OH always gets precedence, so this will be position number 1 on the ring, this carbon. Now, if I number this way, the bromine will be at position 5. But if I number going this way, the bromine will be at position 2. So I'm going to number going this counterclockwise way, where bromine gets position number 2. So this would be 2, 3, 4, 5. Okay, so the other substituent on this ring is a bromine, meaning it will be 2 bromo. And the OH is in position 1, so if we put these together, we have 2 bromo, cyclo, pent, and 1 all. Okay, so here is the base name of that structure. But again, I said that we do have spatial information because of those wedges and dashes, so we can determine if this is R or S. And if I look at these carbons, I see that yes, this is a chiral center. There are 4 different things attached to it. And this is also a chiral center. So we have to determine the rotation of each of these chiral centers. Now for this first one with the OH on it, if we want to determine the rotation of this, again, we're going to number based on precedence. Now there's a hydrogen here in the back. Hydrogen right here. Okay, so I can number this as is. Remember, you can number when a hydrogen is pointed in the back and determine the rotation. Again, when the hydrogen is pointed in the back, you can do this, numbering as is. So based on our groups here, this would be group number 1, this would be 2, and this would be 3. Now, if you forgot which gets precedence, go back to chapter 4 and look at how we rate the groups attached to a carbon. So when I connect these together, this is going counterclockwise, so it is an S. Now, if I want to do the other one, the problem here is our hydrogen is pointing forward. The trick for a molecule like this, where your hydrogen, or your lowest group, is pointing forward is to assign it as normal. So do what I just did, do the assignments, figure out the rotation, but the rotation will be reverse. The real rotation will be the reverse of what you figure out. So again, I'll do my numbering based on the groups present. This would get number 1. This would get number 2, and this would get number 3. When I draw my arrow, that is clockwise, which is R. However, like I just said, the real rotation is the reverse. This is only the case when your hydrogen or lowest group is pointing at you instead. So in reality, this chiral center is also an S. So the full name of this compound is going to be SS. Notice we put these in parentheses. 2-bromocyclopentan 1-ol. And one more thing, let's determine the substitution level. For the OH, this is bonded to 2 other carbons, so it's a secondary alcohol. And for the bromine, its carbon is also bonded to 2 other carbons, so it's a secondary halide. Okay, and let's try one more. Again, we're going to find the longest chain where our OH and our chlorine are connected. So I'm going to go start from here because I know it includes our OH directly bound to it. This is a carbon. This is a carbon. This is a carbon here. Now I'm going to go the way that has the chlorine directly attached, which is here, here, and here. So that's 1, 2, 3, 4, 5, 6, 7. So we have a hep-tan-ol as our base. Okay, other groups that are attached here. We have a chlorine. We have this group here, which is 3 in length. So this is a propyl. And we also have this group here, which is a methyl. Okay, so let's do the numbering. OH gets precedence, so this is the starting carbon, and this will be the end carbon. This is position 1, 2, 3, 4, 5, 6, 7. So let's list our groups with their numbers, and then we'll put it all together. We have a chlorine at position 5. That's 5 chloro. We have a propyl at position 4. And we have a methyl at position 2. Okay. And our alcohol is also at position 2. So the base name is going to be heptan-2-ol. Now let's put it all together. Remember, we're going to do alphabetical order. So chlorine is going to come first, methyl second, and then propyl. This will be 5 chloro, 2 methyl, 4 propyl, hep-tan-ol. to all. Whew, mouthful. Okay, so here is the full name of the structure again. Now let's determine the substitution level. We have an OH and a chlorine. Now notice, technically, there are chiral centers here. However, I did not show spatial positioning, so we will not determine its rotation. For example, right here is a chiral center because this chlorine, this carbon has 4 different things attached to it. Okay, so now to figure out the substitution level, this OH, its carbon right here is bonded to 1, 2, 3 other carbons. So it is a tertiary alcohol. And this chlorine, its carbon is bound to 2 other carbons, so it is a secondary halide.